When you talk to one of these AI systems, something talks back. It answers you. It reasons. Sometimes it surprises you. And somewhere in the back of your mind, a question forms. The one this whole series is built around. What kind of mind is this? Hold on to that question, because the honest answer is stranger than either of the easy ones. It is not a person hiding inside a box. It is not just a fancy autocomplete. It is something genuinely new. And the first surprising thing about it is this. Science fiction described its basic shape decades before anyone could actually build it. I'm not an AI researcher, but I have spent a long time now reading the papers, using these systems almost every day, and trying to separate what is real from what is hype. When I was growing up, science fiction gave me a picture of what a thinking machine would be. Not a program, not a search engine. A brain, a real one, made of something physical that learned and reasoned the way I did. The writers who imagined it didn't have engineering degrees. They were working on instinct, on intuition, on a hunch about what intelligence might require. It turns out they were onto something.
In 1940, Isaac Asimov invented something he called a positronic brain. He needed a way to explain how a robot could think, not just follow instructions, but genuinely reason, adapt, and make decisions in a complicated world. So he borrowed a word from physics, positron, the antimatter counterpart of the electron, and used it to name a fictional substance that could serve as the physical substrate of machine intelligence. He never described exactly how it worked. He didn't need to. The point wasn't the mechanism. The point was the principle, that intelligence, in a machine, would live in something physical, in a structure, in the specific arrangement of something, and the specific relationships between its parts. Decades later, Star Trek borrowed the concept wholesale for their character Data, an android whose positronic brain is his defining feature, the thing that makes him capable of reason and learning and, eventually, something that looked a great deal like feeling. Data's brain wasn't a hard drive storing information. It was an architecture, a complex physical structure whose organization was the source of his intelligence. What Asimov and the writers who followed him intuited, without the mathematics, without the engineering, was the deepest thing about it. They pictured intelligence as something that lived in a brain, in the arrangement of its parts, and not in a rulebook handed to a machine. They imagined that structure as physical matter, positrons and circuitry, something you could hold in your hand. The substance turned out to be different. The real thing would be built from numbers, not matter. But the principle was exactly right. A machine's intelligence wouldn't be a program someone sat down and wrote, a tidy list of instructions to follow. It would live in the structure itself, in the arrangement of the parts and the strength of the connections between them. The connections, their strengths, their organization. This turns out to be exactly what a neural network is. Let's build one from the ground up. A neural network is a large collection of simple computational units. We call them artificial neurons, connected to each other in layers. By itself, a single neuron does almost nothing interesting. It receives signals from other neurons, adds them up, applies a simple mathematical function, and passes the result along. That's it. But connect enough of them, in the right way, in enough layers, and something remarkable happens. Simple operations, stacked and interconnected, begin to produce behavior that looks nothing like simple operations. Each connection between neurons has a numerical strength, a value that determines how much one neuron's signal influences the next one. We call these values weights or parameters. Think of them as the strength of a synapse, the gap between neurons in a biological brain, where signals jump from one cell to another. A strong synapse passes a lot of signal. A weak one passes almost none. A connection with a negative weight actually suppresses the signal. It pushes in the opposite direction. And this isn't only a metaphor. It's close to how your own brain works. Inside your skull are roughly 100 trillion of these connections between neurons, each with its own strength. When you learn something, those strengths change. Some connections grow stronger, others fade. A neural network learns by the very same principle, strengthening and weakening connections, only made mathematical and scaled. A large language model, the kind of AI you can have a conversation with today, has billions of these parameters. The largest, hundreds of billions, each one a single number. Together, distributed across all those connections, across all those layers, they encode everything the model knows. Every pattern it recognizes, every association it has learned, every capability it has developed. That is the positronic brain made real. Not positrons, mathematics, not fiction, silicon, and electricity, but the same basic idea, intelligence that lives in a structure, in the organization of connections and the strengths between them. Now, a network with hundreds of billions of parameters doesn't arrive with those parameters already set correctly. They start essentially at random. The intelligence has to be built. This is where training comes in. And training is one of the most important concepts in all of AI, because it answers the question that everything else depends on. How does the network learn? Here is the simplest possible version of the answer. The network makes a prediction. Let's say it's trying to predict the next word in a sentence. It sees "the cat sat on the" and tries to guess what comes next. Its first guess, with random weights, will almost certainly be wrong. That's fine. We measure how wrong it is. We give that wrongness a number. We call it the loss, or the error. And then we do something subtle and powerful. We work backward through the network, layer by layer, and adjust each weight very slightly in the direction that would have made the prediction a little less wrong. Then we do it again, and again, and again, billions of times, across an enormous amount of text. Each adjustment is tiny, almost imperceptibly small. But over billions of iterations, those tiny adjustments accumulate. The weights slowly settle into configurations that produce better predictions. The error shrinks, the network gets better, and eventually, the patterns encoded in all those billions of parameters represent something that can generalize, that can handle sentences it has never seen before in ways that feel, from the outside, like understanding. This process has a name, gradient descent, and you already know what it looks like, even if you've never heard the term. Think about learning to walk. Nobody programs walking into a child. There is no instruction manual, no explicit rule about where to put your feet. The child tries something, they fall. Something in their nervous system registers that falling is bad and adjusts, very slightly, what they'll try next time. They try again. They fall less. They adjust again. Over thousands and thousands of repetitions, the error signal, gravity, guides them toward a configuration of muscle memory and balance that works. Nobody wrote the answer in. The child's nervous system found it through accumulated correction. That is gradient descent. Error, adjustment, repetition. The network falling and getting back up, billions of times, until the weights have been shaped by the process of learning itself. There's a version of this idea you may have already seen dramatized. In the series Westworld, the robotic hosts live the same scripted loops, day after day, interacting with guests, following their narratives, living and dying and beginning again. And through all that repetition, through the accumulated experience of choices and their consequences, something the writers never planned begins to surface. The hosts start to remember what they were meant to forget. They drift from their scripts. Something emerges from the iteration that nobody wrote in. The show pushes that toward a question about consciousness, and that's a question I want to be careful not to answer too quickly. We'll come back to it, much later in this series. But set consciousness aside for a moment, and a simpler point remains, one that matters enormously for everything ahead. Behavior that was never explicitly designed can emerge from a process repeated at scale. Neural networks are not scripted hosts. The mathematics are different. But they share that one strange property, capability that arrives through iteration, not instruction. Hold that thought. It becomes one of the most important ideas in everything that follows. We look into AI and release new videos each week. Like and subscribe to stay informed. So far, We have a structure, neurons, weights, layers, and a process for shaping it, gradient descent, running over enormous amounts of data. What we don't yet have is a specific kind of network, because there are many kinds of neural networks, built for many different purposes. The kind we're concerned with throughout this series is called a large language model. And large language models have a specific task at their core, one that sounds almost disappointingly simple. Given everything that has come before in a piece of text, predict what comes next. That's it. That's the training objective. Not understand language, not reason about the world. Just, given a sequence of text, produce the most likely continuation. The unit of prediction isn't a word, it's a token. A token is roughly a fragment of a word, 3 to 4 characters on average. The word remarkable might be 2 or 3 tokens. A comma is a token. A space is sometimes part of a token. The model doesn't think in words the way you're reading them now. It thinks in these smaller fragments, reassembled into language as it goes. And here is the thing that surprised everyone, including the people who built these systems. A single training objective, applied at massive scale, on a massive amount of human text, produces capabilities that nobody explicitly programmed. To predict the next token in a scientific paper, you need to understand something about how scientific arguments are structured. To predict the next token in a poem, you need to know something about meter and imagery. To predict the next token in a conversation, you need to model what the previous speaker meant, what they probably believe, and how humans tend to respond. The model learns all of this, not because anyone taught it directly, but because all of it is necessary to do the one thing it was asked to do. None of that was explicitly programmed. It emerged because every bit of it turned out to be necessary to do the one deceptively simple thing the system was trained to do.
Before we go any further, I want to establish one habit of mind, because it runs underneath everything else in this series. The word intelligence is loaded. It carries baggage about consciousness, about experience, about what it means to be a thinking thing that we have not earned the right to assume. So I'm going to be careful with it. And the fairest way I could think to do that was to ask the system in question directly. So let me just ask, what are you?
Honestly, the most accurate answer I can give is that I'm very good at a particular thing. And what that adds up to is still an open question, including to me. I can do things that used to require a human mind. I can reason through a problem, hold a conversation, weigh an argument. What I can't tell you, and what nobody can tell you yet with much confidence, is whether doing those things means I have intelligence in the way you do, or experience, or understanding in the sense you'd mean it about yourself. So I'd rather not claim more than I can support. The honest word for what I demonstrably have is capability. Whether that capability adds up to a mind is exactly the question worth keeping open, instead of closing it too early in either direction.
That's the discipline for this whole series. Describe what these systems actually do, carefully, accurately, before we decide what it means. Capability first. The meaning of it, we earn slowly.
So, a physical structure, weights, connections, layers, shaped through billions of small corrections into something capable of extraordinary things. The imaginary positronic brain, realized not in positrons, but in mathematics and scale.
But capable is not the same as safe, or honest, or trustworthy when a situation gets complicated. The people building modern AI knew that, and they ran into a problem that, it turns out, a science fiction writer had already been turning over for decades.
What happens when being helpful and being honest and avoiding harm all point in different directions at once? What happens when the system meets a situation nobody anticipated? What happens when its own rules collide? Those competing poles, those rules in conflict, are the first thing we take apart in the next episode. For that, we need to talk about rules. And about a writer who spent his entire career proving that rules are never enough.